The trick is, are they still clapping when it's over? All right, can everybody hear me okay? All right. There are like just 4 small Python files at that GitHub repo. If you want to pull them down at a couple of points during the presentation, I'm just going to turn you guys loose to hack on those for a few minutes. There's no pressure. It's not a test. They're not very long. I'm not sure who came because I got responses back from some of the people that signed up, and then not all of them showed up. I know that I had everything from I've already built a Django site to I've not written a single line of Python. So trying to like find the balance in this presentation was really tough. So if you fly right through them, sorry. If you're having a problem with them, we can arrange for you to actually push stuff back up, and I'll look at it after class and correspond with you over email, or we can get a drink or whatever it is and talk about things. So does everybody have that needs it or wants it? Okay. Idiomatic Python. Yep, we have the, I've got to do the About Me slide, right? Some of this already went out in the bio. Been getting paid to fool around with software since 1989. I've programmed in about a dozen languages badly, and Python I've finally gotten to mediocre. And that's okay, because Jacob Kaplan-Moss, who is one of the inventors of Django, gave an entire talk about PyCon, about he's a mediocre developer. And everybody needs to quit looking for rock stars, because when you give mediocre guys a chance, this is what they produce. So currently I'm independently contracting. I've been doing that for about 5 years. Part of it as a contract CTO for a startup, part of it in a small consulting company with some friends, part of it just on my own. If everything continues to go swimmingly, in about 2 weeks, I'm going to come in from the cold and end up working back for the man again for a while. I'm a co-organizer of the Central Ohio Python user group, CoPy. Has anybody here ever been to CoPy? Yeah, so you look familiar. So, so if you're interested in Python, we have a local user group. It meets monthly, the last Monday of the month, over at Pillar Consulting, which is in the ground floor of the Smith Brothers hardware building, right where 670 dumps off near the convention center. So it's, like I said, last Monday of the month at 6 o'clock, except for November, December, because that falls near the holidays. We typically just have a social sometime in the beginning of December to cover those 2 months, and we won't meet at Pillar. It'll get posted on the website, which I foolishly didn't stick up here. I'll add it in at the end somewhere, but it is cohpy.org, not hard to find, just Central Ohio Python, copy.org. The other thing that group does is something called Dojo. The Dojo meets at Panera Bread in the community room. It's the Panera Bread that's on North High Street at the edge of Clintonville, near the big UU church that's up there. And it's unfortunately Friday evenings, so that kind of rules a lot of people out. But folks get together there, and it's just sort of an open hack night, right? So it started out as sort of more formal training for newbies, and then just kind of devolved now to people bring things at whatever level they're working on and just hang out and work on it, whether it's trying to teach themselves something or actually work or scratch an itch. And the idea is if you get stuck, you have other people there to talk to, whether it's you find somebody that knows more about the subject than you do that can really help you out, or you're just rubber ducking them or whatever. So, I mean, those are 2 local resources, if you want to push your Python further, that happens every week. I'm also an organizer and past chair of the PyOhio conference. Has anybody here ever been to PyOhio? Anybody here ever heard of PyOhio? PyOhio actually happens right here in Columbus at the Ohio Union. We had our 9th year in July, next summer will be our 10th anniversary. PyOhio is tied with PyGotham, which is in Manhattan at the United Nations, for the largest regional Python conference in the United States. We had about 450 attendees this past year. It's 2 days, 4 tracks of talks, a lot of really sharp people from around the region that you have the opportunity to meet and interact with, from here, Cleveland, Cincinnati, Indy, Chicago, Pittsburgh. About half of our attendees now do not come from Ohio. They're from the outer Great Lakes region. And we always have a few stragglers from God knows where. We've had folks from Australia the last 2 years come to Pi, Ohio. We had somebody come from Argentina this year. About 3 years ago, we had a guy from Ireland and a guy from France. So go figure. We also usually pull some heavy hitters, guys that are writing libraries that you've heard of, or regular U.S. PyCon speakers. Brandon Rhodes, who's the current PyCon chair, has been a past keynoter for us. Lars Lahn, who was the closing keynote at PyCon 2016, has been a past keynoter for us. Kenneth Reitz has spoken. Simon Willison, one of the co-inventors of Django, has spoken. Just a whole crew of people. So it's a really great conference. It's a really good opportunity to network. It's a really good opportunity to learn more about Python from community leaders and some of the folks that are writing software that you end up using every day if you start using Python regularly. So that stuff over with. On with the show. What makes good code? There's a lot of different philosophies on what makes good code. I'm going to share mine. There are basically two things. First, the code does what it's supposed to do, right? It actually fulfills the business need. It doesn't have weird edge cases or squirrely Heisenbugs, or, it is solid code. When you give it certain input, it produces that output. The second quality that good code needs, we sort of fish around for how we describe that, right? It's beautiful code. It's easy to reason about, right? It's succinct, or it's terse, or, it reads like English, or whatever you want to say, right? These different qualities that really come down to how easy is the code to understand and maintain later. My favorite way to describe that actually came from a guy from Xerox named Fred Krantz, who was my first boss and mentor at my first grown-up job. And his description of that quality is, the code is written as if the maintainer who takes over your work is a psychopathic serial killer. So if you just keep that motivation in mind, all the rest of that stuff about like beauty and expressiveness and stuff just falls in line. Just think the Dexter of programming is coming after you. So, what's an idiom? That seems pretty simple, but I've actually had people, when we've talked about idioms or idiomatic code in their contexts, not actually understand what we're talking about. So the word idiom usually refers to actual spoken language or read language, and there's some formal definitions up there that I cribbed from the dictionary. The one I want to center in on is that middle one, so we'll pop over to that. A form of expression natural to a language, person, or group of people. And I think when we talk about idioms in programming, we're talking about expression that's both natural to the language, the programming language, but we're also talking about expression that's natural to a group of people. And there's a really good example of that is not Python. So here we are at a Python class. I'm weird like that. I'm surprised I wasn't wearing my Pittsburgh Tech Group shirt or something here today. And the first code sample we show is actually Ruby. And you basically have a list, and there's two ways to iterate over the list. I kind of like that first one because it looks a lot like Python. But everybody that writes Ruby every day writes the second one. So over time, the lower example of iterating over that list became the idiom that everyone used, and it crowded out the other method to the point where almost nobody except someone who Googles the wrong thing on the web would use the first form. And in fact, there are now things that you can do with method chaining on that list that you can't do in the first form at all. So they used to be pretty equal in terms of what you could actually express with the code, and that's now diverged. So you have an example there of both a language idiom and a person idiom in programming, right? Everybody in the Ruby community zeroed in on that second one and kind of converged. And so that's kind of what we're talking about. When you have more than one way to do things, what is the sort of normal expressive way that the community kind of converges on. Does everybody know about the Python Easter eggs? So, okay. I'm going to do two of them. You can do the third one on your own if you would like to, because it will hijack my browser, and I don't want it to. The first thing is there's this construct in Python, sometimes where advanced features that are officially going to be in a future version of Python are backported experimentally to an older version. You have this from __future _ import foo, where foo is the new thing, and then you can use it, or sometimes it will even step on an older version of that library, and it changes the library semantics a bit. By the way, when in Pythonese, when you see methods that start with __, if they then end with __, they are what are called magic methods on objects, built-in stuff that belongs to the objects, and you typically never write methods that are named like that. We'll talk about it a little bit later, but while there's no real private methods like there is in Java and C# or functions in Python, there is a way to do some information hiding, and there you just have the double underscore on the beginning of the method. Don't get too focused in on that now, just when people talk about those methods, they'll often say dunder. It's a dunder method, and it's because double underscore is a mouthful to say. So if you hear somebody that programs in Python talking about dunder add, he means the built-in add method on an object. So I can remember. This is kind of one of the gag ones. From future import braces. Syntax error, not a chance. Obvious sort of gag there on Python's white space. For those that are brand new to Python or haven't ever, was anyone here, any of the folks that said, I've never written a line of Python before? Okay. So you know about like significant white space in Python at least? Okay, so yeah, that is Guido's little joke about like when and if significant white space will ever go away in Python and be replaced by braces. That's one of those things that everybody loves or hates. One of the things I find hilarious is I talk to a lot of Ruby people that hate the fact that blocks are white space delimited in Python. But if you look at well-written Ruby code, it's indented just like Python. It has, the UN stuff all over it, but it's hard to tell. Anyways, the other, the real important Easter egg is import this, which ran off the screen. Yeah, it's the Zen of Python. Has anybody here not ever seen or read or heard of the Zen of Python? Because if you've all seen it or heard it before, we'll just skip on by it. Anyone? All right. And then the last one, if you do import anti-gravity, you get a nice XKCD cartoon. But like I said, it hijacks the browser away from this presentation if I do it, so I'm not going to do it. But if anybody wants to, go right ahead. Okay, everything's an object, which means I shouldn't have actually run away from here because I wanted to play back in the REPL for a minute. When I say everything is an object in Python, I mean everything is an object. That's the integer 1. If I do dir 1, I get all this. 1 is actually an instance of integer that's an object with all these dunder methods on it that do things. If somewhere in this mess there is, add, if I actually do 1 + 1 under the hood, what is actually happening is that the one on the left's add method was called and passed the one on the right into it as its operand. And then it returns a new integer. Almost everything that you do in Python, that's how it's actually working under the hood. So anytime you're using operators, assignment, plus, minus, equality stuff. Under the hood, methods are being called on objects. There are no primitive types in Python itself. So in a weird sort of way, you can make the argument that Python is actually more object-oriented than Java or C# or any of these other languages that we think of as OOP. Although you're not constrained to just write in that manner in Python, under the hood, that is what is happening. In fact, you can go all the way down to, let's see. Object is sort of the base object that all user derived classes, and so object has a class of type. Type is an object. We can also do this. We actually grab the object's class attribute, you get the same thing back, type. But the interesting thing is, what if we take that one step further? And now we're going to get the class of type. Type is actually way under the hood, right? It is not just a class or a type, it is an object itself. It's Python's God object. And I'm not going to go through it here because it's a weird syntax you'll never use, but you can actually use type to dynamically construct new classes on the fly and then instantiate them as objects by calling it as a function. So we're just going to skip right on by that. But the point I'm trying to drive at, because I think it's one of the things that's key to actually understanding what's really happening in Python code, is everything is an object and everything is working by essentially calling methods on each other. Any questions so far?
Functions objects.
Yes.
Yeah, like JavaScript.
Yes. Absolutely everything is an object. We already did that. The second thing that you kind of have to grok to sort of start to develop a deeper understanding of Python is all the assignment in Python basically create names. There's no concept of a variable that actually holds a value. So if I assign hello world, the string hello world, to A, I've essentially got a name A that points at the string hello world. If I now assign A to the name B, I now have two things just pointing at that same string. If I change B, I don't actually change that string. I just take the name B and point it at something different. And now those two things point at different actual objects, and the hello world is still there. So they're sort of like pointers, in that they're actually a reference to something. But they're not exactly, because there's no way to sort of reference or dereference them, so you change the value of one, and then when you check both pointers, they now have that new value. It just doesn't work like that. Assignment always just attaches a new label to a thing. Now, where people get confused is that assignment is not the same thing as modifying a composite object. So just a little code snippet here. We start out with a list, then assign to A, then we assign that list to B through B equals A, and then we change B. Just the diagram we saw, if we print A is still its original value. Makes sense. This is where people get tripped up sometimes. Okay, so I go ahead and assign A to C, and then I say C subscript 0 equals 7. That is not an assignment to C. That's basically changing the underlying list. Lists are mutable objects. So now I've just changed the first thing in the list. So, and that is where people get confused about how assignment actually works in Python. So we're not actually assigning to the name. We're subscripting the list and replacing the value there, essentially. Does that make sense to everyone? Okay. At any point, like, this is, I guess, more of a class than just a presentation. So if somebody has a question, you're confused, or just actually, even if I say something wrong, because I'm not perfect, I learn something new about this stuff every day. Like interject, say, "Hey, wait a minute," and we'll go digging around.
Are there other languages where arrays are treated more like literals, or where this wouldn't be the case, and they actually have copies of the object? But you know what I mean?
Not that I'm aware of, not at that level. I mean, most things actually, yeah, you can have more than one thing pointing at an array and index into it and change it, and both things end up seeing that change. But people see that and then get confused why the stuff up top where you're, doing A and then B equals A and then changing B, and why doesn't that change? Then the other thing is like pass by reference, pass by value arguments. In Python, those names kind of work like composite objects in Java. So if you're used to programming in Java, you can sort of think of argument passing as working that way. You're actually passing by value, but the value is the reference. Nobody's ever seen it. This is the Python version of the classic determine if you're passing by value or not. And it's, without doing any other special things, can you actually change what's outside the function? So foo is a string spam, bar is eggs. We have a little swap function. By the way, this is not the Pythonic way to do that, but this maps towards the way that it's done in most other languages, so I just did it that way so it's clear that that's what I'm doing here. So we just swap the values around, and in the function definition, we call the function, and then after the function returns, we actually see what we got, and in fact, nothing has changed. Okay. Did I go backwards? Yeah, no, this was just a repeat of that, showing that the names don't matter. I was like, what did I do here? So there's no magic to, the naming. If I change the argument names to match the variable names, everything works exactly the same way. That's a question that's come up in the past. Okay. Here's just another example of the same thing. If I create foo123, and then I create a reassignment function and I pass that in. It doesn't actually, inside the function it's reassigned, but that has no effect outside the function. So when I get to here, oops, I'm still, no matter what you do, you get the original value of foo at the top here, trying to modify it inside that function, which is kind of what's expected after we just looked at the last screen. But there is a way to actually do that. So Python has a global scope that you can use to reach up and touch those variables if you need to. Like if you actually use this kind of stuff to maintain state all over the place, you deserve the unholy hell that you're going to get. There's one useful use for this we'll look at a little bit later, which is Python does not have a good singleton pattern as a class or an object. If you need that kind of functionality, often the simplest way to do it is to make an importable module, i.e. part of a package library, behave as a singleton. The globals are actually global to the file scope that they're in, not the entire application. So if you make a global inside an imported library, it's only global inside that library. And then you can write some methods that reach in and out, set that value. And if you have some sort of singleton-like global state, that would be why you would want to use that. But yeah, so if you set foo spam and then you do global and then set it inside, notice I actually have to call global foo inside the function. I can't actually pass foo in and also declare it global. That will actually raise an error. and you call the do mod, and yeah, now you actually do change the value of that outer scope name. Okay, that was probably a little confusing because I know I was a little rough talking about it. Is anybody like completely lost at this point? Okay. We now begin our feature presentation, iteration. So let's go poke at some code for a few minutes. Okay, is that big enough for everybody to see? All right, so first thing up here, this is an abomination. Who would do something like this? And the answer is, this looks a lot like the first time I iterated over something in Python about a decade ago. Python is just so flexible that people coming from other backgrounds tend to just start looking at the syntax and grabbing for what works, what they can map to what they've already been doing. So this will work, right? I have a list up here of strings. I set a counter to 0. I set the max to the length of the list, and I just do a while loop over it. Keep track of the counter, increment the counter, right? It's as close as you can get in Python to a classic, C for loop iterating over something. Yeah, that's terrible. This is better compared to the above because you are using essentially Python's for iterator to iterate over the list, but you're still keeping track of the counter yourself. So when I do len dogs, it gives me the length of this list, and then range creates a list of those numbers. And so now I'm doing for I in over and iterating over that list of numbers, and then using that to index into this list. This is a lot more common. This is like crazy stuff that people that have been messing around in C or old versions of PHP try to do. Common to see in Python code, somebody just doing this. And it's kind of silly because if you're just iterating over the list, you don't need to count anything because Python just does it for you. So the Pythonic way to actually iterate through some sequence is just for thing in sequence. So for dog in dog, print dog.
If you were modifying list contents, is there a better Pythonic way to do it, or that you would default to that middle? You had to add to or something, I don't know.
Yeah, typically if you're gonna try, modification in place is not usually a good thing to do in Python. So, I mean, there's a way to do the middle thing so you can get indexes if you need them, as opposed to trying to do this bottom thing and mess with stuff as it comes around. So that's a good question, and the answer is we'll be there in just a minute. Okay.
This may be a dumb question, but you said that frame, like on line 15 and 21 to sort outputs.
Yeah, exactly. There's some better ways to do that clutter up the example code. So if you actually run these, you can see output. So when I get done here, I'll check this in, and everybody can muck about with this stuff as well. I just left those in there so the output's pretty if you actually do something, if you just run the file directly. Yeah, normally you'd want to add some stuff off the print statement here, but I'm trying to keep the actual code we're interested in kind of clean. So.
Is there a console, like something like that, instead of just doing print, or something for like debugging purposes, so you're not doing a function or like one of the directives versus like,
Yeah. So I mean, the actual really correct way to so for one thing. There is actually a low-level debugger in Python, so you can actually call into a debugger and step into the debugger. Like using PDB is a little bit beyond, like that would be a 2 or 3 hour class today. That's one thing that you can do. I mean, you can also set that up so that it will drop into the debugger when you're running stuff from the REPL on an error. The more canonical way to do this is just set up a logger, right? So if you set up a logger and set on your debug statements, and actually we'll talk about it a little bit later, but there is a sort of the standard Java logging API. There's an analog to it here, so you can just call logging.debug and whatever you want to put there, and only if you've actually got your log level set to debug will you see those. And then you can set up one of your log handlers to be, if you're running in the REPL or just running file from the command line, to be a standard out. And you can also duplicate that to a file so you capture everything right at the same time, however you want to do it. So yeah, I don't talk a lot about log formatting here because that's another thing that's like kind of a squirrely mess, and we could burn a lot of time on it. So yeah, another thing that we see sometime when people want to come back to playing the range len trick is trying to figure out how to do things like reverse code or sort code, right? So this thing right here basically generates the range numbers backwards. So now when you index into that, the numbers are running backwards, and you'll back up through the list, right? Except we just have this handy built-in function that does that for you. So, and you're back to that same for, foo in thing iteration pattern. Same thing, there's one for sorted as well, which leads you to think that this would be the best way to do this, and it's actually not a bad way because you can chain these functions, right? So for dog in reversed sorted dogs, but it's doing extra work because actually you can just tell sorted with an argument that you want it to sort in reverse. So I don't expect you to remember all of these things, but part of the takeaway from this is when you're trying to do something, even if you're in a bit of a hurry, try to take a poke through Python's documentation and the standard library documentation and figure out if there's already a canonical way to do what you're trying to do documented there. Because the guy who comes after you, once again, he will thank you for it. And he might be a serial killer. So we were talking about what if you needed the index for something, like you're going to modify the array, or just even if you wanted to know it. But what if you need that number because you, for whatever silly reason, you want to print out what position in the list these things are. Once again, playing with range and len are the bad way to do things. There is a function, a built-in called enumerate, and when you hand a list into enumerate, it sends back, okay, real quick, who says tuple and who says tuple? Tuple, tuple, show of hands, does anyone? Even
try to pronounce it. I just read it.
It is a core data structure in Python, and even like senior Python people argue over how to pronounce the stupid thing. So I tend to float back and forth depending on who else I'm talking to because it just makes the conversation flow better. But anyways, so when you enumerate a list, for everything in a list, it sends back a two-tuple. The first thing is the index, and the second thing is the actual value. So that lets you do this kind of mess that you would normally try to do with range and len and count yourself here, and just once again do it by magic. This illustrates another thing that we'll talk about a little bit more later, which is unpacking. I don't have to enumerate for everything in the list. It's going to return a two-tuple integer, the thing, right? I don't have to grab that as a single name here in this for right here. I don't have to grab for whatever and enumerate, and then when I'm using it down here is like whatever subscript 0, whatever subscript 1. I can actually unpack the tuple right into two names and then just use them directly. That is a little Python nicety that makes for a lot cleaner, more self-documenting code, because when you're, and that works for most sequences, not just tuples. If you've got like a 8 or 9 things, you probably don't want to do that. You probably want to think about how to better structure your code. But if you just got 2 or 3, that's beauty, because you can capture them in names that make sense instead of capturing it, the larger structure in one name and then having to subscript it to get at the values you really want. The code becomes more self-documenting, less complex. Another interesting thing here about enumerate is there is a little hack here, because lists start indexing at 0 in Python. Actually, all sequences do. And I want my pretty list to actually start at 1. So up here, I actually was getting before I printed it. But actually, if you go read the doc on enumerate, you can actually set the start value for it. So by setting the 1 here in the enumerate call, I get rid of this ugly number plus 1, and I just call number. So once again, sort of the lesson here is, I don't think you'll remember all of this, but when you're trying to do these things and you've not been doing them for a while, go take a peek at what's in the Python documentation for built-ins in the standard library. It will save you a lot of heartache. Where do we want to go next? Oh, let's talk about multiple sequences real quick, because this is another thing where people start playing with ranges and mins and lens to try and figure out. We've got 2 lists here. We actually want to enumerate over them and pair them up. One is shorter than the other, so we're just going to leave the excess dangling, right? So here we've got for I in range of, well, I got to take the min of the length of cats and the length of dogs, so I know how far I want the loop to run, yada, yada, yada. Once again, there's a built-in zip. Just zip takes sequences, and however many things you pass into zip, here it's 2, but you can pass n things in, n sequences in, it generates an n tuple on the other side, just grabbing from each list and spitting the tuple out. So, so you can just do for cat, dog in zip cats and print out cat, dog. Whereas over here, not only do we have this ugliness up here, but when we get down to here, right, we're having to subscript into cats and dogs to get the stuff that we want, which is not as nice. Everybody cool so far? You can actually do this kind of iteration with dictionaries. So for people that don't know, dictionaries are Python's standard hash type, so key value. Most of the time, like the examples here, you will see people just using strings or occasionally numbers for dictionary keys. You can actually, and that's mostly what I've done here for clarity, but just so everybody knows, you can use anything that is immutable as a dictionary key. So the tuple constructs we've been talking about that some of these built-ins spit out, unlike a list, tuples are immutable. Once you change them. So you actually use into a dictionary. There's certain object types, frozen sets. There's a whole bunch of stuff that you can actually spit in as dictionary keys, and that becomes useful sometimes in doing comparison lookups, especially since, if we remember, functions are objects. You can actually have these weird keys mapped to a function, do a lookup, and call the function that way, which sometimes you get into cases dealing with weird external data or with somebody's badly written library where you find yourself actually pulling out a trick like that. But for the most part, that's not real standard. To get the keys from a dictionary, if you just want the keys, it's the same iteration as any other sequence. So if I do for key and owner dog, it just spits back the keys. It doesn't concern itself with the values. Okay, I made a copy of the dict here because if you run this, there's a little bit of evil here. And you're seeing something else the first time, which is you've got try except block catching an error here. If you try to do this, you for key in owner dog 2, just like in owner dog, and then you say if key equals some value, we want to actually delete it. So we're actually deleting something in the dictionary as we're iterating over it. You can't do that. Basically, in some dictionary implementations, this will cause the dictionary to get in a screwed up state, and it will behave bizarrely. In older versions of Python, you could throw other weird errors or even sometimes crash the interpreter. They were squirrely and hard to debug. So now you're just not allowed to do that. Now, if you actually do want to do something like that, what you have to do, there's a thing called a view into the keys. So owner dog is the dictionary. Keys gives me a dynamic list of the keys. So actually, if we were doing some other fancier stuff, you could, if you change the dictionary, so if you set a name to be owner dog keys, and then you change stuff in owner dog and just went back, and you don't need to call owner dog keys again, you just go back and look at that name, right? That structure, the view will have updated. But you can't iterate over views either because they're dynamic. So what we actually do is we do owner dog keys, which gives us a view of all the keys, and then we instantiate that into a list. So now I have a separate list of the keys. And now it's safe for me to actually iterate over that list. And if the thing in the list matches what I want to get rid of, I can delete it back in the dictionary because I'm not actually iterating over the dictionary. I'm iterating over a list that is a copy of the dictionary's keys. Follow? Okay. Okay. You can like this, obviously. So we already know how to iterate over the keys, so I can just go for owner, and so that gets me a key, and then I can print this fun line here, and I can get the owner, and then I can actually look it back, and that will give me the value, which in this case is another, which is the kind of dog, right? That is all right, but it's not really the preferred way to do that. It actually, not only is it a little uglier than the canonical way, but it does extra dictionary lookups. So if you're doing this over very large data sets, there is, for this it's a joke, but there is a performance penalty if you start doing this kind of stuff over big data sets. Once again, we use that magic tuple unpacking, and we call items, which gives us key value for everything in the dictionary as a two-tuple. So we just tuple unpack for owner, breed, and owner dog items. And once again, we don't have any funky subscripting we have to do here. It's just nice, clean. I want to print, for every one of those, I want to print the owner, and I want to print the breed. I'm going to talk a little bit about what's going on under the hood while all this iteration is happening. So for loop over iterable sequence is basically sort of a syntactic shorter for a bunch of object stuff happening under the hood. Anything that is an iterable sequence will have this dunder iter method. You can either call it directly to get an iterated sequence, or here we've made two of them. Here we call them an iter over the sequence. Both of those give what's called an iterator object over the sequence. And if you actually print the type of these things, this is what it'll actually output, right? List iterator, because it's an iterator over the list is the class of the object. Okay. Once you have that iterator, it has a next method. Every time you call next, it emits the next thing in the sequence. And that is essentially it, other than if the iterator is not infinite, eventually it'll raise an exception called stop iteration. And the underlying iterator stuff that we're running when you do for foo in something actually just catches that stop iteration and halts the iteration without the error ever bubbling up where you see it. But that is what is going on under the hood when I do for foo in something where something is an iterable sequence, right? I actually take the sequence, I call iter on it to get an iterable, and then I just call next over the iterable over and over again. Here we're just doing it in a while loop, essentially, and it just keeps running. Did you have a question? Okay, go ahead.
So basically, you're never going to be writing it like this. It's just this is what's happening under the hood.
Actually, you can, and we're going to discuss that next. This is what's happening under the hood, but you can use this methodology to actually make your own custom iterators. Although there's a better way to do it now. Back when this first became available in Python, this was actually how you did this stuff. Okay, my iterator. Okay, yeah, so this is just a quick, more easy example of what's going on when you do for something over something. You're basically getting the iterator while true. This actually has the iteration stop in it. The other one would just run forever and eventually throw an error because it was going to run off the end of the list. This actually catches a stop iteration and breaks cleanly out of the while loop, so you never see the error. So this, when you do this, this is as close as you can get to what's happening under the hood in pure Python code. Question? You can actually create iterators. So this is a really contrived example, but I created an iterator class. I initialize it with some kind of sequence of strings. Here we've got the good old dogs list again. I set a count. I set a max to the length of the sequence I passed in, and I define two methods, iter, dunder iter, and dunder next. So what this thing does is it becomes both iterable and an iterator at the same time. So you don't have to define two separate objects to make that little thing happen that I talked about before. Because when you call that, if we look back here, protocol 2, when I do this part, dog iterator, iter dogs, when someone does that to my iterator class here, to an object of that class, it just returns itself. It says, hey, you're trying to get an iterator over me, but I am my own iterator, so here, you can have me. And then here's the part where it is its own iterator. And basically, every time something calls next on it, it looks into the initial sequence that you passed in. And what this thing actually does is it figures out the position of the thing in the list, and whatever position it's in, it adds spam to the front that many times, and then it outputs it. But let's actually, if you run it, that's what happens, right? So, but yeah, doing these for real is sometimes pretty useful. I did some Python code that was dealing with something called HL7, which is a medical software message passing format, which you can think of as nested CSV, basically. There's multiple delimiters instead of just like commas, and they go down. And so, yeah, we actually built custom iterator objects to make it easier to iterate over those things in depth and reassemble them from Python objects and stuff like that. So,
I have a couple questions.
go ahead.
One is, what is sequence of strings?
Oh, sequence of strings is just whatever you're passing in when you, so, okay, so this is Python's initialization method for a class. So sequence of strings, when I instantiate the class to get an instance of it, that is just what I'm gonna, that's the name of the variable that I'm gonna pass in so I can initialize things, right? So, and all we do with that, we do a couple things. So here we're setting instance variables. When you see that self dot something, that's basically how, when you're referring to an instance of a class, an object in Python that you've created, that's how you get a reference back to the current instance from inside the instances, that self. And it's not magic. If you actually pass something different into the beginning of a init here, you can change the name of that. If you do it, people will hate you because they won't be able to figure out what your code is doing. So using self there explicitly is like one of the biggest idioms there is in Python. Because most Python programmers don't like dealing with classes in the first place. So if you make them extra hard to deal with, they'll extra hate you. Yeah, so basically, we set this variable to the initial thing that we passed in. Then we're setting a count value to 0, and then we're setting the max value to the length of this list that we passed in, how many items are in the list. So we can keep track when we loop down here of what we got. So if you see down here, for value in my iterator, I never explicitly created a name that held this instance. But classes are callables in Python. There's no new keyword. You don't have to say foo equals new my iterator something. You just call them like they're a function. You pass into that call whatever their init method expects, if it expects anything, and you get an object back. So when I go my iterator dogs here, I don't have that class my iterator. I now have an instance of the class. I now have an object. And so for value in my iterator is looping over the object. Does that kind of clear things up?
Yeah. And my one other question was, it looks like you're using Sublime Text, but how did you execute Python?
Oh, you can actually wire up some plugins, a Python interpreter, and to actually do this, as well as a couple of other fun things. I have them turned off because they're annoying when you're typing and messing around. But as we all know, Python is not a compiled language. Even if you're using a full-blown IDE like PyCharm, it has to do a lot of introspection and tricks to give you the nice things that tell you your code is formatted wrong or has bad syntax or whatever. You can also use that interpreter to run a couple of linters called pyflakes and pylint over the code, and it will catch a lot of the kinds of errors that you would normally catch in an IDE if you're running in Sublime or Atom or Vim or Emacs or something of that nature. So that is all running in my Sublime. I will go look up the information I have on how to configure Sublime for doing this, and I will email it out to the class at the some point over the weekend here, or stick a link to it in the GitHub or something so you guys can find it.
Can you do static methods then?
Yes, you can, actually, and we will. They're not really static methods. You can do class methods that you call on the class, but yeah. But there is this notion of a method that's attached to the class and not an instance. But usually you can actually call them on the instances as well. So you can't call instance methods, which is what we've defined here on the class, because you have to actually instantiate an object to call them. But class methods, what Python considers to be class methods, can be called. Okay. And then what was the last piece that I wanted to look at here? Oh, I think that was it before we went on to the next bit. So let me zip back to slides and make sure I'm where I want to be. Okay. So some takeaways from all the stuff that we've just blasted through. Iteration is how you get things done in Python. If you see an explicit counter while looping, there's probably a better way to do things. So if you see somebody doing tricks with len in range or at len in next range or whatever to get a counter variable to loop over stuff, there's probably a better way. So if you're in code that's doing that, take a look at the documentation, refactor. Well-written Python looks like business logic, or whatever your domain logic is. And that's back to when we were doing some of that iteration and we were passing things out as tuples, so you could just do the unpacking assignments and have nice names for things. instead of having to get that thing out of a function as a sequence itself and index into the sequence with numbers to find stuff. And you know, well-written Python, you kind of try to push your I/O out to the edges, and that's a lot of times where object stuff comes in, because you're trying to keep track of I/O state and other weirdness, and write functional code internally that's nice, clean, and looks more like your domain logic for whatever your business domain is. Okay, generators. More code. This looks familiar because generators started as, and this is mostly what we're going to cover with them. Generators started as a syntactic sugar functional way to make custom iterators. So what we're basically doing with generators is the same thing that we did in that my iterator example, where we had a class with dunder and dunder next and all of that fun stuff. You can just do that as a function, and it's called a generator in Python. Now, this is actually a terribly ugly generator. And the reason that I wrote it, this first one this way, was this is the closest you can get to the behavior of the myIterator class that we wrote. So the code that's doing things here pretty much looks, you know, maps pretty closely to how that iterator had to work. So sequence, we do a while true loop, we keep track of everything. The one difference is, since we're not, like, we don't have a dunder next method here, is, you know, how does, you know, if you remember under the hood, when something is consuming a sequence using the iterator protocol, when they're doing down here for value in my generator, under the hood, they are calling that next over and over again. So in a generator, how do I describe what next produces? And it's the yield statement. So using yield in a function instead of a return value, or no return at all. So Python always does return something, on some, unlike some languages that can have a situation where they don't return anything. But unlike, I think, Ruby returns the last evaluated statement. If you don't explicitly return something from Python, it just returns none, which is Python's null object. So it always technically returns something. But here in the generator, instead of return, we do yield. So every time through the loop, what happens is when I first call the generator, this while loop starts running, and it runs down to where this yield is and spits out the first value from the loop. The generator suspends execution and passes execution back to the code that's iterating over the generator and waits for it to call next again. When that code calls next on the generator again, it runs another iteration of the loop and over and over again, right? And every time it just runs a loop, hits yield, hands a value back. It keeps track of all the state, right? When it suspends execution, all this state that I'm doing here that I was using, you know, instance variables to keep track of in the class version of this, that's just all book kept for me by Python. So I don't have to worry about any of this. I can just almost treat it like a function, except I've got yield in the loop. And since we're actually using this code down here to run over an initial passed-in sequence, just when we hit our endpoint, instead of using stop iteration, we just break out of the loop, and this thing doesn't yield anymore, and we're done. So you don't actually have to explicitly raise stop iteration or any of that nonsense when you're in a generator. Does everyone kind of follow along so far?
I have a question. So,
Okay.
in the case of a return statement, when it would be reached, it would just stop execution and return. Is it the same way with yield, and it won't do that count plus one until it comes back? Or
Right. So the count plus one actually happens when next again. So it stops right here, hands this to the caller, which is this for value in, one value out, and prints this thing. value and save again. And that happens over and over under the hood till the generator runs out. Okay, I had a better version of that I wanted to look at. There we go. So that's pretty ugly because remember, you know, in Python we don't really want to see counters and we want to see stuff that looks more like business logic. So we can do a little bit better here by going back to our old friend enumerate. And we have this multiplier value we still calculate because enumerate is going to give us a 0 where you want a 1 and so on and so forth when we're doing that multiply effect. Spam out. But yeah, now we just have a nice clean thing here. And since we're not keeping the counter ourselves, we don't have to increment that counter after the yield statement. Does exactly the same thing, a little bit nicer code. Change. So rather than you know, doing all the work in one generator, I can have a generator here that does count text pairs. So for count text in whatever was passed in, right, I generate my spam string and fill it out. And that's all this is concerned with. It's actually the input to this is the count number and the breed text. So it's getting, this generator is getting a sequence, and every sequence is like 1 Husky, 1, 2 Beagle, 1, 2, 3 Doberman, right? So down here, we have a separate generator that actually runs over the initial sequence of strings, and for a string in that sequence of string, it yields the length of the string and string. So we broke up finding the length of the string with calculating the spam, whatever, into 2 shorter, easier to follow generators. And then we just actually can go ahead and set a name to all of those chain generators. Now, the reason I have this print gen here, let's see if I can find it in this. I think it ran off the edge and it won't let me get back. That's just so when you run this, you'll be able to see what gen is, which is a generator object, right? So when I do all this stuff, I'm not getting a list back yet. I'm getting a generator object. So all of this code, this my generator 3, which is up here, and the string length and strings, which is up here, you know, doing all this work, okay, it actually does not execute at all, just sets itself up. So I get down here and do for value in gen, which iterates over this outer generator. Generators are lazy, which is their other big advantage to doing other iteration in Python. With other iteration in Python, you're dealing with lists and tuples and dictionaries. If you have to deal with large data sets, right, you're constantly amassing temporary huge chunks of data, you know, a list of 500,000 items or whatever. So, you know, if you're dealing with massive chunks of information from database, parsing terabytes of log files, you can use this generator pattern to make all that iteration lazy and set up a whole chain of I pull in a line from the log, I split it this way, I look for something else here, you know, and just run that all back, right? All that stuff never goes into memory because there is a way to actually iterate through a file as a generator. So basically, very low memory overhead. And early versions of generators traded speed for that low memory overhead. But as more and more work has been done on Python internals, generators have gotten pretty close to just iterating over something already in memory. And in certain cases, they can actually be faster. So there's no reason to not use them unless they're slow and you have ridiculous amounts of memory to play with. But typically, the kind of speed up you're going to get from doing that, if you're really worried about that, means you should probably be doing whatever you're doing in C or something like that. You probably should just get out of Python for those purposes. Just a little bit more chaining. This is just a nice little thing that was on the the CoPy mailing list from one of the CoPy regulars named Jim Pryor when he was messing about and teaching himself generators. And this is just a generator that basically calculates Fibonacci. It doesn't just send out the last value, it sends out the whole sequence. But as it generates the numbers in sequence, it only actually emits the ones that are even. So that's what this whole little bit of code here is doing. But you can actually break that into separate bits. So this here is an infinite Fibonacci generator, right? You can call this till the cows come home, and until you run out of memory or some other resource on your box, it's going to keep generating Fibonacci values. But, right, I'm not doing this into a data structure like a list, where if I call that, I am going to go into an infinite loop and it's going to start filling that list up. Remember, this is lazy. So even though this will generate infinite Fibonacci till the machine resources run out, it doesn't do that unless I actually start looping over it, you know, with something else that it itself tries to be an infinite loop. And of course, I don't want to do that. We have another generator that just looks at a number and says, if you're even, I'm going to yield you. That's another thing about yield, right? So if you have an input sequence, you're doing some work, and you're yielding, there's no requirement to yield an output value for every input value. I've got a sequence of numbers that are coming in. I'm checking to see if they're even. I don't want the odd ones, so I just don't do anything with them. I just let them evaporate into the bit bucket. There's no need to like write else clauses and handle the case of I don't want to do something with this value. You just drop it and yield the stuff that you're interested in. Everybody follow? And then the last bit here is actually this is the outer thing that we run so we can cap a value, and actually when we chain these things together, that underlying Fibonacci generator just won't run forever. And then you can chain them all together just like we did in the other example. And if you run this, they're basically the same as, we know, there's nowhere I run this, but it provides the same output as this even Fibonacci, the whole thing. So we're running a little long here. So a couple things. I'm going to just like sort of skip the bits where I had files for you guys to play with. You're welcome to carry them home with you, noodle around with them, and bug me about them if, you know, if it'll help you with anything. Or you're welcome to actually just email me and say, wow, this was way too easy. Give me something harder next time. But does anybody need like a 5 or 10 minute break to, or be good to drive on here? Just to hit the bathroom and reset? Anyone? All right. Okay, so quick takeaways on generators. Generators are a much more straightforward way to create your own iterators. Generators are lazy, and generators can be chained to provide nice separations of concerns. I spent a lot of time on iteration and on generators. They are a key component to getting the most out of Python. Like the rest of this stuff, if we didn't get through any of it, and that was all you took away, is, you know, this is how you manipulate and transform data, right, in Python. You can think of everything. I have a set of data. I need to run some transform on it, get another set of data out. I can chain that stuff together, consume low memory. That's, you know, the most important thing that we'll talk about today. Now, we have only scratched the surface. Literally, there's a gentleman who's one of the best Python trainers in the country. His name's David Beasley. He gives a lot of corporate classes. He speaks and gives classes annually at PyCon. He has 3 different presentations on generators that were done as PyCon classes. I think the total amount of time is somewhere around like 6, maybe 8 hours of a presentation like this on things you can do with generators. So there's way more. You can send values to generators to make complex workflows. We've been yielding values out of generators, but you can actually put an expression on the right side of that yield, and you can call next on the generator, and in the next call, if you pass a value in, that goes into the generator and you can do something with it. So you can actually use that technique to set up sort of like a fan-out, fan-in workflow where instead of pulling data, you're pushing data through the generators. Generators are pretty much at the heart of how coroutines work in a couple of the async libraries in Python. And yeah, that is, so Beasley's first presentation is all about doing stuff, both pull and push with generators over data sets. Like sysadmin types will just, love that stuff. His second one is all about this idea of doing coroutine stuff with generators. The third one is a fun one. It's more coroutine stuff with generators. He sort of, in 1 3-hour class, implements a half-baked, completely written in Python version of Python's new async IO library, which is kind of like one of the 2 big Node.js for Pythons. So he sort of builds that lightweight version of that with generators in about a 3-hour class. The resources for that at the end. If you want to learn more about this stuff, go watch those videos. Yeah, but we've not even, that's why I spent so much time on this. This is a big deal if you're trying to learn both how to write idiomatic Python and what you can do with Python. Recursion. Do I even want to do this? This is the classic sort of Fibonacci that you might see in C, that you run it and it does recursive calculation, and it doesn't actually try to return the whole list of values, it just returns the last one. That you go look up like Fibonacci in C and you'll find something like this, and that's the Python version of it. Let me see. I am going to just show you real quick. So that's that there. If I run it, get out 55, it seems to work. And give it a real number. And I get an error. Recursion error, maximum recursion depth exceeded in comparison. Python does not do tail call optimization, which means that when you use recursive functions, every call of the function has to go on the stack. So in CPython, every call of that function is going on your stack in C. The way Python is built, that would risk essentially running the stack into the heap or somewhere else it shouldn't be and causing way bad things to happen. So there is just a fixed recursion depth limit in Python. When that stack frame nesting hits 1,000, you're done, and it just raises an error. Now, that limit is something that you can set when you start the Python interpreter itself, right? So there have been people that have written recursive code and changed the limit and used it, and you're playing with fire for 2 reasons. The first is you've just code that's portable in the universe. It just won't run between Linux and Windows, but it will probably only ever run properly in your environment because nobody runs production code with that value changed. The reason for that is changing the value large enough so that you could do the kind of recursion you do. Interpreter, and I'm not sure, there's some squirrely low-level bugs that are responsible for that. But if you fire it up and set that number to 500,000, things will seem to go good for a few days, and then it'll just fall over in seg fault. So people don't do that. And the other thing is, Python is actually terrible speed-wise. To a middle value, like long enough so it just isn't short enough so it doesn't throw that error right away. If I set it to like 100, 150, it'll sit here for minutes. Fan spins up and sounds like an FA-18 taking off. So, yeah, you just, okay. Unpacking sequences, we talked about this already, so I'm going to just like fly by it, right? Instead of for foo in some iterator, you'll see for foo bar in some iterator. That's unpacking. We've talked about all this before, so I'm just going to kind of fly by it unless somebody has further questions on it. Anyone? Okay. Context managers. Okay. If you've ever run across code like this, and I have in Python files, right? Here's a routine that takes a file path and prints stuff out of the file. So we get the file path, we open the file, we go in a while loop that just spins until we run out of input. So line is file read line. If we actually got a line, we print it. Eventually, we're going to get a blank line at the end. When that happens, we break, and we close the file. Does anyone know the fundamental thing that's wrong with this code right here? What happens between here and here if an error occurs? Yeah, the file stays open. Now, in CPython, a lot of times when anything that points to the file falls out of scope, it's not being used anywhere, and it's eligible to be garbage collected, it'll actually go ahead and close the file handle as well because it knows it's not reachable. Also, when the process exits, the handle closes, so if you're running batchy stuff. Those are implementation details of CPython, which is the reference version of the interpreter. But there's no guarantee that you'll actually correctly close file handles at all if you create this case, say, in Jython, which is running in the JVM. So in the old way, you had to put all that stuff in a try block, right? And you don't necessarily really care about the exception here. You might actually want the exception to bubble up if the exception occurs. So you don't actually catch the exception with an except clause in your try block, but you do have finally. Finally is code that in a Python try block will always run no matter what happens, whether the block completes successfully, whether an exception is raised and handled, whether an exception is raised and bubbles up to the caller, doesn't matter, finally will run. And so you can close your file. And I have this big, ugly, non-Python-y code that I'm looking at here. So that's why we have context managers. Context managers are basically syntactic sugar for that whole mess that you saw up here. That's one of the things they do. More broadly speaking, context managers let you save state and restore it. Or even more broadly than that, perform cleanup actions, whatever they may be. Even if that is, I save some state and I want to restore the state as cleanup. So there's a lot of things that you can do with them. The thing that you'll see most in more modern Python code is right here. We replaced all of that with open file path as file. That with there denotes that we're entering a context manager, okay? So now I just do my for line in file, print line. If anything happens in these 3 lines after the file is already open, it'll close. And I don't have to worry about it. I don't see it in the code. It's not cluttering me up. If you know, when you grok how context managers work, you just don't have to think about that stuff anymore. It just happens for you. You can make your own context managers. This is a big, hairy class. This is actually some code off of GitHub that another gentleman wrote. I've actually used a heavily modified version of this in production. Mine does some extra stuff to the file stream and then compresses it, whereas this is just basically the raw bytes. But what this thing is basically doing is, when you open a file, right, you can use the normal Python file open semantics, and under the hood, it'll actually go out to AWS S3, find that file, read the file all at once, throw it in a C-string I/O buffer, which is a string in memory that you then can access using the same methods that you would on a file object. So it has essentially the file object interface. And that lets you sort of treat this whole mess as a file, right? When you start the object up, it grabs data. While you're working with it, you think you're dealing with a real file, but you're just dealing with this memory buffer. And then when you get all done and you close that file object, it writes everything back to Amazon, right? So the cool thing about this is how you make context managers. You define a dunder enter and a dunder exit on stuff. And basically, enter is what happens when that with block runs, and exit is what is guaranteed to happen when the block exits. And so if enter, we return ourself, because remember we're creating a file object here, and in the example I just showed, we went with open something as file. It was a file object that we were playing with. And then exit, we close ourselves. That is basically how you can take anything that supports the file API in Python, or that you build even, and turn it into a context manager that you can use that with stuff. So up here somewhere, I didn't have it here. So, okay. Now, I'm going to show you the simple way to make one of these. Suppose you have this big hairy object that implements the file API, but it doesn't have that enter exit stuff in it, and you're like, oh man, I don't want to modify this guy's code and worry about the next time I pull updates from the Python package index or off his GitHub repo that I stomp back on the stuff, and I have to fork it, and yeah, you can just fix that by wrapping that thing in a context manager. And so there's a library in Python called ContextLib that has a bunch of tools that help you build context managers more simply than having to write objects with the dunder methods. And we're going to import a decorator called context manager. And we'll talk about decorators a little bit more in the future. But basically, we decorate this function with context manager. So it knows, right? That's actually syntactic sugar for wrapping this function I've defined here in another larger function that handles some of the context manager bookkeeping. But then all we have to do is define our function. And what I actually do is I call back up to that file object, right, that this guy created. And there's our old friend yield again. When you're creating a context manager using the syntactic sugar, you yield once and only once. You're not iterating here. The yield is just a signifier that I'm handing you back the thing. If you remember dunder enter in the more complicated version, right? I'm handing you, that's the equivalent of dunder enter. Here's the file I've yielded to you. When the calling code exits that with block, right? Because the calling code would do with AWS open as file and do stuff. When that with block exits, then we advance past the yield, and you just stick any cleanup actions you have after that yield statement. So setup goes before the yield statement, cleanup goes after, and if you've got something that supports a file API but is not a context manager, you can make one in those few lines and then use it the way that I used that with block call all the way back here. It's now supports doing that. Those show up all over the place, actually, because like I said, they're not just for like file type I/O. In threading now, the lock is a context manager in Python's threading library. You can, like I said, use them to save and restore state stuff. You can like make a copy of some list or some name, some other object, and then do stuff, and then in the finally block, restore the thing back again. Whatever you want to do. In the Python standard library, there are context managers for error suppression. So in old code, you would see, often you would see, try, I'm going to do something, and if it fails, I don't care. So you accept, catch every exception, and then you call pass, which just means swallow the error, don't raise it, don't let it bubble up, do nothing, just keep driving on. There's basically an error suppression context manager, so you can do with, I forget what the thing is, but like with errors, right? Or, with suppress errors, I think it is. But basically then everything inside that with block, if it raises an error, it just gets ignored, and you don't have to do the try, except, pass stuff to deal with stuff inside your code there. Questions, anyone? This real quick is just the lock example. This is the kind of stuff that you used to have to do with threading. So you import the threading library to create a lock, and then you had to wrap all the lock stuff inside try finally blocks to make sure if things went bad, the lock actually released and something else could get the lock. Old way, new way down at the bottom. So once I create the lock up here, all the way down at the bottom with lock, do stuff. And when it falls out of that with block, lock releases. This would have been lab 1, but we are way over on time. So we are going right on to dictionaries, and you guys can play later. Okay. Okay, just a little bit more on dictionaries. We've already been using them. We had that example of iterating over the dictionary. We talked about how they are Python's basic hash. So when you create a dictionary, you can actually, before we were using the curly brackets notation to instantiate a dictionary with some values already. So it's like curly brackets, key, colon, value, comma, key, colon, value, comma. You can actually just call dict, which is the dictionary class. And if you feed it a longer sequence, here we have a list, and every item in the long list is 2 tuple, then it will actually go ahead and basically pair those up, key value, and instantiate the dictionary. It's like, why would you want to do that? Because this here is so much prettier. And you wouldn't do that manually. The reason that that's useful is if we go back and remember when we were playing with some iteration stuff, and we had the zip function, which zips together sequences and returns tuples. We can actually use zip with 2 sequences. So dict zip fields order effectively does this, except you're not typing the list out forever. And if fields in order are, 1,000 items each, right here, that just creates the dictionary. Questions? Another cool thing that almost nobody knows about, I talk to like Pythonistas all the time, that they're like, really? So this is a common kind of thing. You'll see it in Django web applications. You'll see it in command line stuff. You have some module defaults. They're a dictionary, right? And I have pretend environ here, which is another dictionary. That's subbing in for actually making a call to OS environ, because I don't want to expose all my environ variables to all you guys, because there's keys in some of them. But normally, to get that second thing, you would call OS environ and get your environment. And then you would have a dictionary of all your environment variables. And then pretend command line is if this were actually a real command line app and I was pulling in the args, I can build a dictionary of what I pull in off the command line. Now, typically at that point, you have to write some convoluted function logic to look into those dictionaries to figure out, like, if I want to know what my screen width should be, like, where do I look? Or the other thing that you'll see people do is just merge all these dictionaries, right? So they do a dictionary merge and create a new dictionary, and they merge all the dictionaries, and the last one in stomps on. So if a key exists in dictionary 1 and dictionary 3 wins as they smash on down, right? A couple problems with that is it's not efficient. But also, if anything changes, that merged dictionary doesn't recognize the changes. It's a new copy. It's a shallow copy, but it's a new copy. So, and even more confusing, if the values of the dictionary are composite objects, sometimes changes to the originals will change those things depending on how the change was made. But yeah, so anyways, slow, confusing. What you can actually do in the collections library, in the Python standard library, and that's another thing I want to mention. Everything that we've talked about today is built into Python. There's nothing that we've hit yet where you need to go like install something to use it. So you can make this thing called chain map, which just under the hood does all the fancy bookkeeping. When I said the first way to do this is to write a function that tries to keep track of all 3 dictionaries instead of merging them. It's already built in to the Python standard library. Once I call chain map on these dictionaries and assign that to settings, I can now treat settings as a dictionary itself, and it will have, one key. So, I passed in logging off as a module default, but in my environment, I had turned it on, right? In my module default, I'm not in debug mode, but when I started this thing on the command line, I turned debugging on. So after I do the chain map, if I go into settings and check those values, right, they'll be the last things that came in. So my debug would be true, my logging is on at this point. And so it's just a nice way to, when you're taking dictionaries from different parts of an application that control configuration state, that you can map them all together without merging. Any changes to the underlying structures are reflected in the chain map. So if your environment changes, the next time you actually check into settings, you'll capture that, things of that nature. Questions? Once again, there is a ton more stuff on dictionaries. Also in the collection modules, there are a bunch of specialized dictionaries that you can go play with. There is a dictionary that maintains order. So normally when you iterate over dictionaries, right, it's a hash. The order you get stuff out in is arbitrary. Order dict, it doesn't sort, and if you modify it, you break the order. But when you initially create it, if you feed in, like when we did that zip list example, the order those things went in, unless you modify the dictionary, will always be the order stuff comes out when you iterate over it. So if you need to generate a hash map, but ordering is important when you iterate over it, that's there. There's another dictionary that is optimized for generating default values. If they don't exist in the dictionary, you can use functions to create default values. So if somebody tries to grab a key out of the dictionary, it's not there. Instead of erroring, it'll build defaults. There's a counter. So you can actually key value into the dictionary multiple times, and instead of overwriting in the key is the item, but the value is just counted. So when you get all done, you can go look at that key, and instead of say you were passing strings in, and you passed key and some string in multiple times, you end up with the count of how many times that went in. So you can use it to basically iterate a common sort of coding exercise is iterate over sentences, split those into words, iterate over the words, stuff them into a counter dictionary, and you can count the word occurrences in a body of text that way. Other data types. Going to zip through this pretty quickly. String and byte, I just want to mention, we've been using a lot of strings in the demo code today. We haven't talked about them very much. In Python 2, you had ASCII strings and Unicode strings. So when you just saw a quoted string, it was actually an ASCII 256 byte, 0 to 255 ASCII string. If you actually wanted Unicode, you had to actually declare it with this, oops, little U in front of things. So in Python 3, Unicode strings by default. So the top thing where it's not, there's no signifier on it is actually equivalent to the U thing in Python 2. ASCII text went away, but there is now a notion of essentially a raw byte data structure where we don't ever try to say it's necessarily text or maps to text, although you can do some tricks to do it that way. It's just literally holds bytes from 0 to 255, a sequence of bytes. Lists, sets, tuples, arrays, and decks. We've talked about this a little bit. We've been using lists all along. One thing that we've not really covered, lists are heterogeneous sequences. You can actually have a list that has different things in it, and they're mutable. So you can modify them. You can insert things into them, pop things off of them, grow them, shrink them, do all kinds of stuff to them. Tuples work a lot like lists, but they're immutable. So once you create one, it's done. Lookups into tuples are very fast. So if you're building a sequence to return and you're not going to modify the sequence, you're just going to consume it back in the upstream caller, tuples. Yeah.
Go back a slide. What's the real benefit of comparing a string as raw body versus default? Like, what's the true payoff there?
Because sometimes you really do want to just handle, like in Python 2, you could have like an ASCII string, and you didn't really care that those bytes map to letters. You were just using it as data values, right? You know, and you know there was a way to access like that byte value as hex or as as base 2 or whatever. You can't do that in Python 3 because if you're spitting arbitrary bytes into that string and just treating it as bytes, you might accidentally generate a Unicode sequence for a multi-byte character, and then things are going to get weird because once that's in there, things don't necessarily work the way you expect them to. Like say you think you've written 50 bytes into that Unicode string, but there's but the Unicode string represents characters, and you've hit a Unicode escape sequence. So now you have like instead of like 1 byte equaling a character, you might have like 6 or 8 bytes that equal a character. So if you do len on that, you're going to get the character count, which doesn't equate back to the 50 bytes that you think you wrote in there. So bytes is a way to do that kind of manipulation and declare, hey, it's just bytes. If I write bytes into this thing, it's bytes. If I want to iterate over it, I'm going to get 1 byte for every run of the iterator. I'm not getting characters. If I want to count it, then the number of bytes is what I'm going to get back. That's not necessarily true for Unicode. Unicode represents characters. Some Unicode characters take more than a byte to represent. So that's the whole thing. Did you guys follow that?
So
Okay.
is that common practice that you actually declare? Like I'm just curious, like in Python 3, how common is it that
To do raw bytes, it's actually pretty rare. Yeah.
that's what I was
So
wondering, like,
yeah. Yeah, I mean, there's it literally is. I'm manipulating some string-like data as raw bytes for some reason, and yeah, there's usually not like a reason to do that.
But is that something like a pro Python expert?
Yeah, yeah. This is the kind of thing when like people are trying to write exploit code and stuff that they get into. I've not run across this in the wild yet. I mean, I've seen it in like, presentations and stuff, but I've not seen production code using bytes yet. I'm sure there is some out there that does. Okay. So, yeah. So, and then we have sets. Sets, right, must be unique. But there are mutable and immutable sets. So you do have sets that you can add stuff into, and then you have ones that are just frozen like a tuple when you create them. And then you have decks. Basically, decks are list-like objects that are optimized for use as queues. For those of you who are like C buffs, under the hood in the C reference interpreter, lists are essentially data structures indexed by an array under the hood. Decks are doubly linked lists. And the purpose of decks in Python, the doubly linked lists with some extra fast methods attached to them to pop stuff off the ends and push stuff off the ends. So they're first in, first out, last in, last out, last in, first out, all those queue types. So if you're using those, use a deck and not a list. So there's just a lot of code here that we've already seen similar to otherwise that are demos of lists and tuples. Just real quick, the set stuff. If you notice my set, into the set constructor, I'm passing a list that has duplicate values in it. When the set comes out, it'll just collapse all the duplicate values. It's a quick and dirty way to actually clean all the duplicates out of a list is to essentially pass the list into a set constructor, and then if you took this my set and passed it back into a list constructor, you get a list back, and all the duplicates would be nicely cleaned out of it without you having to write any code to find them and kill them yourself.
Does it auto-sort? Does it auto-sort the values?
No, sets are unsorted, so that is sort of the one drag about that is that if you care about the list sort, that won't necessarily work. But if you've already sorted the list some way, you can resort it after it comes back out again to get the order you need back out. But if it's an arbitrary order that you care about, yeah, then that trick doesn't work. Good question. Go ahead.
How do you know if it's a dict or a deck or a list? Is that one
Okay.
declared, or how do you?
So yeah, yes. So there's a two-layer answer to that question. One is that so when you declare these things, so a list is square brackets, right? Or you can also instantiate the object by calling it a class list, L-I-S-T, and you can just call it empty for an empty list or pass stuff into it to generate a list. A tuple, basically, it looks like parens. Oops, you'll see, I keep wanting to grab that. You'll see that starts with parens and ends with parens when I create a tuple here. That's one of the few things in Python that's visual syntactic sugar. The actual thing that creates a tuple are the commas. And if I left those parens off, I would still get a tuple. It basically takes those individual things and does packing. We've talked about unpacking. It does packing into the tuple. So you get one anyways. And then set is normally called with the set operator or the set class to instantiate a set object. There's an alternate method. If you notice when you print it out, you get the curly braces that you also get with the dictionary. You can also use that to create a set. So the rule for curly braces for inline code is inside the curly braces, if you have key colon value comma key colon value comma, it'll build a dictionary. If you don't have that key colon value, if you just have value comma value comma value comma value comma using the braces notation, it builds a set.
Do they have like a type definition where you can do a variable name dot type or type of?
Yeah, you can actually, but that is part two of that question, which is, and I don't know if we'll get to it here because we are running short on time, but the real answer to that is you should almost never, ever care. So I like talked about iteration and generators and how iteration really is at the heart of how a lot of Python works. Basically, to write decoupled code, when you're writing code that iterates over stuff, okay, you should not care what you're getting. when you're creating those things, you should care what you're creating because there might be a specific reason why you prefer a tuple, because you want it to be immutable. You don't want people to change it. You might want it to be a set to make sure that there can't be duplicate values. You might make it a list because you know at some point the caller or some other code, if it's like in a stateful object, is going to change it. But usually the consumer of sequences doesn't care. About the only time that you normally care, outside of weird edge cases, is if you might be getting just a string. Because if normally you're expecting a sequence of individual strings, a list of individual strings, a tuple of individual strings, strings are sequences as well, and they obey the iterator protocol. So if you accidentally start iterating over that raw string, you're going to be getting individual characters as substrings, and it's probably not what you want to do. So one of the few times that you actually might be checking your input before you do something with it is if you're writing code that iterates, and there might be a chance that you hit strings instead of something else. But actually, let's skip all the set stuff. Real quick, blah, 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 sets, you can, if you create two sets, you can do all kinds of mathy stuff with them, right? You can find the intersection, you can find the exclusions, right? They behave like mathematical sets. We all took math in high school, college, right? The reason, and Dex, we talked about that. If you see stuff like this, I created a list, I'm appending stuff onto the list, I'm popping stuff off of the list, I'm inserting stuff into the end of the list, I'm grabbing stuff from the end of the list, you probably want a deck. It's a lot faster. And the last thing, real quick, in data structures, arrays. People use the term list and array a lot when talking about Python, casually, but there really is an array data type that is separate from lists. And they're homogeneous, and each element is either a numeric value or a single Unicode character. So, and using them is the same kind of thing as when you're using byte strings. It's like data manipulation of the kind that you rarely do in Python. Yes. Yes, it is. All these data types are either a built-in, they're built into the core Python interpreter, or they're somewhere in the standard library. And then name tuples. I want to mention these real quick. These behave just like a tuple, except that you essentially create them so there's a fixed naming structure. So they're sort of kind of like immutable dictionaries, but you can use dot notation to actually get to the properties. And the primary reason to use these is, once again, self-documenting code. Right, so from collections import name tuple, I create this thing, shirt order equals name tuple, shirt order size color. Shirt order is now a name tuple class, right, whose name is shirt order and expects two values, and it's going to set the first value to the size parameter and the second to color. And so function that returns a tuple, instead of returning just red comma large like I would for a normal tuple, I can return this shirt order red large. And so as that flows through the code, you just see shirt order floating around instead of this unnamed tuple thing, and you need less comments to actually sort of figure out what you're doing. It helps the code self-document. And then also, once again, you don't have to subscript the tuple. Even if you don't want to use unpacking, because say like the tuple is like an 8-element tuple, and you don't want to have comma, 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 comma left, like trying to unpack all those 8 things into nice, clever names. If you use name tuples, they're just properties on the tuple. Oops, and you can grab whichever ones you want. Okay. So I probably have another half hour to crank through. Are we at a hard stop here? Can we go on, Kevin? If people want to go on, it's up to folks.
I'm flexible, it depends on the rest of the room here, so.
Okay.
I'm gonna I'll have to leave in a little bit.
Okay. Are you taking off, or you just?
Oh, I'm just gonna.
Okay. Yeah, if everybody wants to take like 2 or 3 minutes here to. So real quick, I wanted to talk about comprehensions. comprehensions are syntactic sugar for creating some of the data structures that we've been talking about. The point of comprehensions is to have less code. They're one-liners. And also, comprehensions in general should read more like a mathematical equation than code. So classic here's a function version where we get a list of words in and we return a new list where the elements in the list are the length of the words, right? So pass the word list in, I create a new list here for words in the word list I pass in. Into this length list, I append the length of the word. I get all done, I return my new list. So down here, word lengths, get word lengths, words, calls all this mess up here, right? Exact same thing. Comp word lengths equals, I open my bracket just like I'm going to create a regular list and close with a square bracket. But instead of list elements inside, I have a statement. Len word for word in words. So that's literally it. So for this words thing, right, up here that I defined, for word, an individual element in words, I'm going to get the length of the words. And that just builds the list up right there on that line. To me, it's much easier to read, right, than trying to puzzle out what this thing does. Once you understand the comprehension notation, you're like, oh, okay, I'm creating a list, and I'm getting the length of a word for every word in words. Not hard.
Could you execute this one? I'm kind of curious what the difference is.
Okay. Yeah, they're the same thing. That's the point. Yeah, they're the exact same output. They're different lists. They're two different lists in memory, but they're the exact same output. So you can also do that with sets. So here I define a function that takes in two iterables, it makes sets out of them, and it computes the intersection by ANDing them. And I can call that function and get the set back. Or I can do a set comprehension. And once again, I can do word for word in words, the first list, if word in words 2, the second list. Now, in this particular case, this is a little slower, so I don't know that you'd want to do it on scads of input. But if you're dealing with, a couple thousand, I think, once again, this is a lot clearer. It just almost describes in sort of half English, half logic what you're doing. Give me a word for a word in words. So emit the word for a word in words if that word's also in words too. And once again, we get the exact same output.
Is point one or after the stacking the default?
I haven't even looked. I don't pay much attention to, like it's almost like wall clock time, and that's being added on by, it's actually being added on by Subversion. So it's actually calling a Python interpreter under the hood, running this as a one-off batch job, and getting the data back on standard out or standard error. And that's kind of like the almost click to clunk of like if I typed it in and when it exited. So yeah, have you been seeing that a lot? Yeah, and it literally might be like the drag of I/O between Subversion and firing up a copy of the interpreter, because it's not even keeping a running interpreter back there that it feeds stuff to. It literally has to start the interpreter every time it wants to do this.
0.1 seconds is a pretty long time.
It is.
You typically notice that.
Yeah.
I think it seems like that's some bug in that output. I think maybe that's the lowest.
It's possible, although when I was doing some other stuff, yeah, it may be the lowest it can go. I've definitely made it go farther, when I've been. Yeah. But the other thing is like, this is convenient kind of for running stuff in here really quickly to show you guys, so I'm not doing a lot of jumping around, but I typically don't work this way. So I've never even paid attention to that, to be honest about it. Same thing, dictionary. We can actually generate dictionaries. So We pretty much here are, with get stats, we're actually instantiating an empty dictionary. We're globbing the file structure wherever this is running, looking for .python files there. And we're creating a dictionary where the key is the name of the file and the value is basically the sort of OS stats, which is kind of like the C stats structure. And it's almost a one-to-one map. Or once again, right, there's dictionary comprehensions. So I can say file colon, that'll be the key, OS stat file for file in glob for Python files. And once again, much clearer. Now, you can nest these comprehensions and you can make more complicated if statements and if else statements. And over here, where you're doing, like if we go back to this where I'm just saying, len word for word in words or whatever, you can do all kinds of calculations. So, I've essentially, like the whole point of these is to be easier to read. And I've seen some of these where I've looked at them and going, okay, this isn't Perl. What are we doing here? The idea isn't to cram as much on a line as you can. So a good rule of thumb for me is if I can't describe what it's doing in 1 or 2 sentences in English, then I probably should rewrite it as a function or a generator instead of an expression. And I actually skipped over one real quick, but same thing, generators. Here we have a generator, and the parens here, len word for word in words, generator expression, so that is lazy. None of this will actually do anything till I start running for length in over it. So all of that stuff, so basically we have lists, sets, dictionaries, and generators are all, you can all create those via expressions, that nice one-line syntax. Questions? Okay, talked about that. Real quick also, Python does have map, reduce, filter functions. I hardly ever use them, so in 3 they move them around a bit. In Python 2, 2 of them were built-ins and one was in a iteration library that was in the standard library, and I don't even, if I wanted to use them, I'd have to go look them up. There's nothing you can do with them that you can't do with either actually building a function or a comprehension. Sometimes, especially if you are trying to write code in a more functional style, they're useful for chaining things together. But yeah. And then just real quick, here's an example of, this one's not even terribly complicated, but at first glance it's like, okay, what's that do? Comprehensions are supposed to make things more comprehensible. Let's do some functions and friends stuff real quick. Okay. Definition. This is a function. Function prints. We've been using them all class. Def. Functions are first class. Other function. Prints. How long have we been using them? And then executes other functions. Okay. So was it you that were asking earlier about, somebody was asking about our functions objects. Yes, they're objects. They're first class. You can pass around and use them as data like anything else. And once you get your hands on the data, you can actually execute them. So when I run this, I'm calling this function. Functions are first class. So there's the parens, so that's being called. I'm passing in this thing right here. This is a function. When it lands inside the function, the name inside the function is other func. It's not this is a func, it's other func. But if I make other func callable by attaching the parens, that function runs. Okay, so you can also do whatever else you want to, all right? You can put functions in a list, And then you can execute them, right back out of the list by subscripting the list correctly. You can do the same thing in a dictionary. Occasionally, those are useful. At a project that I'm working on now, we use a thing called Celery, which basically manages worker processes. So the main Python process feeds stuff into RabbitMQ queue, and the worker processes pull jobs off and execute them. The original default serializer was something called Pickle, which serializes most Python objects. It's also not safe because you essentially are passing executable code around as data. So if somebody actually injects the wrong Pickle object into your stream and you deserialize it and do something with it, there's no guarantee what you really have, right? It's an attack vector. So we switched to JSON. The problem is we have some code where we originally had first-class functions being passed around, and those would get passed through Pickle. And you can't pass a function through JSON. What we were able to do, some of the code we refactored to get rid of that dependency on injecting a first-class function into another function. Where we couldn't, we built dictionaries where we defined a function, and then in the dictionary, name of function as a string, the actual function as the value. And now we can pass the names around, which will serialize as a string in JSON. When we get it out the other end, we can look up the name in the dictionary and execute it that way. So where we need to do some dependency injection, we can still essentially do it, sort of. Both sides in advance have to know what they're dealing with. You can't, but that's true for Celery anyways, actually. Even if you're passing an actual function around, you're really under the hood, even in Pickle, not completely always passing the function the way Celery works. So anyways, so yeah, so those things, they seem weird, but sometimes they are useful. That also allows for, like I said, clean dependency injection patterns. We can have something here, def string lengths and strings, that, for a string in the input, does some stuff and spits it to the output. And we don't care what input or output are, we just call them to get stuff and call them to send stuff, right? So, and then we can define file input as our context manager that returns lines, and we can define the output as the built-in print function and call string lengths, and it will suck data out of the file, print it. And we can actually even cut that even further, just doing the thing as a context manager. So yeah, and this version actually writes to a file. I'm kind of going a little fast here, so questions on that stuff at all? Lambda. Python has a lambda keyword. If you actually work in any kind of functional programming language, don't get excited because it's not really real lambda. It's just a way to do sort of semi-crippled inline functions. People who think they're cool abuse them all the time. Don't. Like, you'll see this kind of stuff. These are the same, def, and these are simple, but you'll see def add 2, return x plus 2, right? The whole point of lambdas for what they do provide is to be an inline anonymous function. So if you're assigning the lambda to a name, you've just done the same thing, except it's harder to read. So yeah, don't do that. Two places that I think lambdas are potentially useful is when you are doing some functional programming, and it's a quick and dirty thing that you're doing, like you can call map, and instead of define a function and passing it in as your mapped function, you can just declare a lambda. So this lambda, so map would iterate over vowels and call the lambda, which the left side of the colon here is declaring the input variables, and the right side is the statement that does something. And this is, lambda is the one place in Python where there's an implicit return. So whatever you're doing in the statement here, the end value gets returned out. But in this particular case, you can do a comprehension that does the same thing and is actually a little clearer. So it really, these sort of become a matter of the programmer's judgment trying to figure out what is the most readable approach for using these. The other way is if I'm defining a function and I expect one of the things in there to be an injected function, and I'm always going to call it, I want to have something there as the default. That way, the user cannot pass a function, and maybe I'll just get an identity back, which is what's happening here, right? This is a function that expects data, and it's going to print the data, but before it prints it, it's going to run a validator over the data. And this little lambda here is just essentially an identity function. Whatever you pass in, it passes right back out. So if I set that as a default, if the caller doesn't have a validator, he doesn't need to validate the data, he doesn't even have to pass one in. That becomes the default, and it runs. Make sense? Sometimes when you are calling those kind of functions, you can pass in a lambda if it's really short and sweet, once again. If I'm only doing this once, maybe I don't want to define a function that's just going to basically get a string and call up around the string and return it. But yeah, if you see complicated lambdas, or you see a lambda where you have like an assignment to a name and a lambda on the right-hand side, that's a big Python code smell. Yeah, so decorators. Real quick, we've talked about how you can inject functions into Python because they're first class. You can also return functions from another function because, once again, functions are just data at a certain level. And that lets you also sort of do function composing here. So this is just a real simple common example. The outer function makeAdder takes a value, and it returns a function that takes another value. And what that function does is take the original add value and whatever is passed in. So, right, if we do add3 makeAdder 3, then whenever we call add3 and pass a value in, we're going to get 3 added to that back out, right? So, follow? So yeah, so it's a classic example of a closure, right? We're closing over the inner function, or the add value parameter here with the inner function. So even though the makeAdder function exits, adder has closed over that add value and hangs onto it and uses it over and over and over again, right? So that's important in Python because we can combine all of this stuff, the idea that we can pass a function in as an argument, that we can create a function and pass it out and make decorators. So basically, we can modify what a function does without touching the code of the function itself. And right here, this is a classic thing here. It's a timer. So we can do timing, pass in a function. The inner function is this wrapper. It calls time. It runs the passed in function, calls time again. It prints out the difference, and then it returns that wrapper function. So, and then I have a function that'll take a while. It's long func. And then before I run long func, I actually, right, long func call timing, this decorator function. So now long func is wrapped by that wrapper, which will run the timer. Now there's an easier way to do this. Down here we define long func 2, and instead of having to do this long func equals and call the timer and pass this thing in, there's syntactic sugar for that at timing. So at something above a function definition is a decorator, and it's a sign that somebody has written a decorator and wrapped the function with it. I have mixed feelings about that. Sometimes it's, it's a little magic, especially if the decorators are all defined somewhere else. You see a function definition, and then it'll just be at this on top of it. Web frameworks use that a lot. So if you're in like Django or Flask code, you probably recognize the decorator and are like, oh, I know what that's doing. It's the auth decorator. So every time this view runs, it'll check to see that I'm logged in. But when you're working in like less popular code, sometimes you're like, well, what the heck does this thing do? Unlike one of the differences, besides language differences, between the Python community and the Ruby community is Ruby tends to like implicit magic a little more than Python, and Python tends to lead towards explicit. Not necessarily verbose. We don't want to be Java, but we don't like a lot of hidden stuff. So mixed bag with the decorators. But yeah, you can, in addition to the timing, you can modify the output of a function by calling the original function and adding some stuff to it, and a whole bunch of stuff here. So I'll just run this real quick so we can see some of it. So yeah, the interesting bits here were we ran longfunc and longfunc2 with timeit on it, so we actually got times out, and that's, yeah, oh no, I see the one. So that's about right because longfunc2 did twice the work. So, and then the other thing is we iterated over a list of names that's on disk here, and we added is a jolly good person. So the original function just would have printed the names. The wrapper added the is a jolly good person bit. Right? So get names with open names text as file, return file, read lines, so it returns the data. And the wrapper actually uses a comprehension, return line strip, plus is a jolly good person for line in some function. Questions? Okay. I'm going to just jump without hitting the slides right to objects real quick because there's a couple things I want to mention. Somebody asked about class methods, and there are also class level properties. Basically, in the class, if you define any properties at the top that don't have the self dot thing, they're class level things. Another thing is Python really doesn't have private methods or properties, but you will see these kinds of things where you have a single underscore and the double underscore. Single underscore is just it's like a friendly warning. It's kind of like saying this is alpha to anyone who may be using this class as opposed to continuing to develop on it. So if I'm writing other code that uses this thing, I probably don't want to grab sort of private directly because the original developer putting that single underscore on there is saying this could change or go away. It is an internal implementation detail, right? But as Guido says, Python is a language for grown-ups. If you really want to do that, it won't stop you, okay? You can freely actually grab that thing. It's the honor system. This is a little trickier. This can still be reached because all it's doing under the hood is doing some name mangling. So I say double underscore almost private equals almost hidden. Under the hood, the object actually changes the name of that thing. So if I'm calling it from outside, I can't get to it. But if you understand how to meta-program objects in Python, you can still get to it. So you really haven't hidden it. You've just made it harder. For that reason, almost nobody ever does this, because somebody who really wants to get the value can still get the value, and it actually makes programming your own code against the thing a little more difficult. So it's very rarely done. We'll skip the demo stuff because it's not that interesting. I just want to point a couple of other quick things out. So we have a bad class object here, and the reason it's a bad class object is when I initialize it, it sets data to none, and then it defines getters and setters on that property, which is a common thing to do in compiled object-oriented languages that have encapsulation, right? I don't want to expose the property. What if I have to do something later to the property? So I expose a method that plays with the property. That way later on, like if I want to add some validation checking when I'm setting the property, right? I don't change the interface because I've always been calling a method to get the value and always been calling a method to set the value. So, right? The thing is, in Python, we don't care. Good class. Just set self data and instantiate the class. And when you want to assign something to the property, you just assign it to the property, just like you were doing a variable assignment. If you want to get the property, you just get the property. And then everybody goes, but what if my interface changes and I want to actually do some validation on the property? In that case, there is a way to do that. There's property decorators. They do let you define sort of getter and setter functions, okay? So we can set self underscore data, and we use this property decorator here, def data, and it returns the self data property, and we can do a setter decoration, and we actually define the same name again, but here we're setting self data, and we actually wanted this function because we're going to force all the incoming data, which is a string, to in this case expected to be a string, to be uppercased, right? And everybody goes, well, that's just as complicated as writing getters and setters, so what's the advantage? And the advantage is, in, say, Java, you write the getters and setters up front, because if you need them later, there's no way to get at them without changing the interface. If you started with direct access to properties, and you have to switch to getters and setters, the interface of the caller to get those things and set those things changes. In Python, it doesn't. The property magic means that I still use these as properties. So I set props data equals more stuff. It just looks like a property assignment. Under the hood, this function actually runs on the data. So you can start with the simple version, right? I don't need to actually validate anything or check anything. I can just let people set the properties. Later on, if you need to add a more complex version, you can add a more complex version that still uses the straightforward property syntax. So it's sort of backwards, right? You can be real simple because you can actually hide complexity later under that simple interface if you need to. So there's no need to go write getters and setters. It's a kind of a contrived example here, but if you have an object that's got 15 state variables you're trying to keep track of, and now you've got to write 30 functions, and that's no fun. And in Python, you don't need to write anything at the initial state. You technically don't even need to initialize the variables if you don't care what happens if code tries to call them and they're not there. Right, if any calling code has some try except stuff that's going to deal with a missing property, then you don't even need to do the initialization in init. The first time you actually set a property on the object, it'll just make it. So, okay. I think we're going to call it a day. There is one more section that I would have liked to talk a little bit about, but we're just out of time. And so maybe what I'll do is we'll talk about that a little bit at the beginning of class next week. It has to do with some questions that were raised earlier about errors and error handling and checking of the values of things. But basically, if any of you guys have ever heard of duck typing, that's pretty much the idiom for dealing with unexpected input in Python. So 99% of the time, instead of when you get input passed into a function, instead of trying to check what it is, or you just do what you're expected to do with it, and you basically stick that inside a try except block and deal with the exception. Python has a very, very good set of base exceptions. So unlike some other languages, I haven't kept up with what JavaScript is doing lately, but I know in older JavaScript, catching an exception and then trying to actually figure out, what exactly the error was could be a hair-pulling experience. In Python, it's dead simple. So, it's very much ask forgiveness, not permission. So we'll go over that a little bit. And then, based on class feedback, everybody seemed to be most interested in looking at a Django project. That was what I got off the initial questionnaire. Not everybody answered it. Is that still the case? That everybody is primarily interested in looking at some Django stuff? Okay. So next class, we will spend about 15, 20 minutes walking through duck typing, how to properly do error handling, and also just a couple of niceties on why you should write your own error classes. And last, we'll talk very briefly about the proper way to do things when you do need to actually understand something's type before you use it. And then we'll dive into a Django project. Rather than just like walk through the tutorial, I actually have something built that I can do a little bit of extra work on, and we can bring in and look at all the parts and pieces. I take it that since everybody here is pretty much a developer, right? If you just wanted to do the Django tutorial, you just go do it. So I think we'll look at something that's put together already and talk about it. So any questions at all before we wrap this up? This is all the... Yeah, I'll add these to the GitHub, actually, so... well, we have some wants, but that was just in case we got there. Last thing I wanted to say, right? Testing. There was no test code in any of this. Python, for a long time, did sort of not have the commitment to testing that you see in the Ruby community. But it is rapidly getting there. The thing is unit test in the standard library is pretty clunky. There is this wicked cool thing called PyTest. If you guys are, and once again, that's something that even other than telling you about it here, we won't even have time to talk about it next week. But if you want to write nice, clean Pythonic unit tests, then pip install PyTest, which will install the PyTest library. It's also another thing that makes me feel a little funny inside because it does a lot of what it does with some under the hood magic that's not obvious to the people that are using it, but it lets you write such nice, clean, lightweight functions to write your tests in that I absolutely recommend it. The unit test in the standard library is based on the old Java JUnit, and it's very much instantiate classes, have setup functions, and do weird assertions, and PyTest just lets you use Python to test. So, okay. Those links were at the end of the presentation. So I'll throw this up on the GitHub. There's more in there that we didn't get to. A little bit of it we'll talk about next week. Thanks for your patience. This actually went a lot faster in practice. So I didn't realize that I would run out of time and go over. Thank you very much. So before I let everybody go.